Okay, so let's say that you are given this graph and this graph only, and you're asked to determine several factors of a damped harmonic oscillator. Now, the only thing that you are given other than the graph is that the mass of the oscillator itself is 3 kilograms. Now, one thing that you can do first is to find the period. In order to find the period is one full cycle of the oscillator. And from here, just eyeballing it, the period would be about 0.8 seconds. And then you'd have to also find your max amplitude or your max displacement. And so for here, the max displacement is 2 meters. And now you're also going to have to find your values of omega, which is your angular frequency, as well as the damping condition B. And you're going to have to find your natural frequency omega naught and the spring constant K.
Okay, so if we know that the period is 0.8 seconds, and we know that the initial displacement is 2 meters, we can use the equation omega is equal to 2 pi over our period in order to solve for our angular frequency. So 2 pi on the top would remain the same, and then the period is 0.8 seconds, and then omega would equal approximately 7.853 radians per second.
Okay, so I know that this code is supposed to be for part F, but I also used it in order to determine my damping constant beta. So after I import all my modules and then I put in all my constants, so the mass is 3 kilograms, the initial displacement or initial amplitude would be negative 2 meters, and that's because if you look at the initial plot that I was given, the original amplitude that it started out with was negative 2. Okay, and then so omega is 2 pi over 0.8 seconds, which is our 7.583 or 853, sorry, 7.853 radians per second. And then in order to determine the damping constant, I used the equation A naught times e to the power of negative beta times t times cosine of omega times t, and then I plotted it in order to get a graph that looked nearly identical to the graph that I was given for this problem. So I tried a bunch of different constants, and the beta that came out the closest to my actual graph that I was given was the damping constant beta equals 0.1. So therefore, my damping constant here for this graph would be 0.1.
Okay, so now that you have found your angular frequency omega, as well as your damping constant beta, which is 0.1, you can use the equation omega is equal to the square root of omega naught squared plus your damping constant beta squared. And then by rearranging that, you get omega squared, omega naught is equal to omega squared plus beta squared, all under the square root. So by plugging in our values for angular frequency as well as our damping constant, we are going to get omega naught equal to the square root of 853 radians per second squared plus our 1.1 squared all under the square root. And omega naught is going to equal 7.854 radians per second. So that's only 0.001 more than our angular frequency, which makes sense because we have a relatively small damping constant of beta is equal to 0.1. So it makes sense that this would only be about 1/1000th greater than the initial omega. Okay, so now we're asked to find the spring constant k, and we can use the equation omega naught is equal to the square root of k over m, and then rearranging that equation, we get k is equal to omega naught squared times our mass, which is 3, which I didn't write up here, but our mass is equal to 3.0 kilograms. And now, so we can solve this equation, so k is going to be equal to our omega naught, which is 7.854 radians per second, squared, times our mass, which is 3 kilograms. And then our k comes out to approximately 185.04. And the spring constant has a unit of Newton per meter. And this kind of makes sense because you've got a relatively high natural frequency, and then you have a relatively small mass, but not relatively small to something like, say, if it was 0.1 kilograms. But still, this should make sense in the grand scheme of this equation as well as this problem in general.
Okay, so here we are asked to draw a phase space diagram or create it using Python. So I just created it in Python, and I showed this earlier for part C where you find the damping constant beta. And so I basically created my phase space diagram here by importing my constants, the mass, my amplitude, my initial amplitude, my omega, as well as my beta. And then I used linspace to do 4 complete cycles like we were asked to. And then I used this equation, x is equal to a naught times e to the power of negative beta times t times cosine of omega t. And then I plotted it, and this was my phase space diagram that I was able to create.